All right, here we go. So first part of lesson 1.4, we are getting into continuity or continuous functions. So a lot of this is going to be seen on page 87 of the chapter 1 portion of your calculus book. So a couple things. We're going to see that if a graph is continuous at a certain point, then it is defined at that point. Also, the limit of the function at that point would have to exist. So a couple things there that would describe something as being continuous. Also, the limit of the function where x approaches c is also equal to f of c. So let me show you some of that with kind of some real numbers plugged in here. So let me give you sort of my layout here of the continuity of a function. So if a graph is continuous, you'll see that it's connected at all points. If it is discontinuous, that would mean you have maybe a hole in the graph, or that would be a removable discontinuous graph. Non-removable is when you have more of a clear break in the graph, usually caused by an asymptote or something like that. So these are both examples of discontinuous graphs. Your continuous graph, one that is connected at all points. A lot of what we see, though, is within a certain graph, we might see that it is continuous within a certain portion of the graph, even though it's discontinuous as a whole. Let me show you kind of an example of that. So this is on page 88 of your textbook here. So right here, so this is obviously a discontinuous graph because there is an asymptote right in here. So this is a discontinuous graph, but if you were asked, is the graph continuous where x equals 2, right? Well, it is continuous where x equals 2. So the graph overall is a discontinuous graph, but it sort of depends on the way they pose the question. So if you see this, the domain from negative infinity to positive infinity, now it's talking about the entire graph. So we can see on this one that the entire graph is discontinuous. But if they were to ask you something like, is the graph continuous from, let's just say, 1 to 2, right? Well, from here to here, we can see that the graph is continuous from 1 to 2, right? So it all depends on the domain that they give you. If it's something like this versus something like this. Or we can be asked, is the graph continuous at a specific point? So if you look at this graph, again, this graph in its entirety is discontinuous, right? So if we were asked, is the graph continuous from negative infinity to positive infinity, we would say no, because there is a hole in the graph. If they were to say, is the graph continuous from negative 1 to 0, well, yes, it would be continuous from negative 1 to 0. If they said, is the graph continuous where x equals 1, right? Well, we would say no, it's not continuous where x equals 1 because of that hole in the graph. So a lot of it just depends on the way they pose the question. So you kind of got to read carefully on those. So let me jump back into these guys. So one of the first functions we get introduced to on this is something called the greatest integer function, also known as the step function. They can give you these type of questions with all different types of graphs. I'm showing it to you with the greatest integer function because you probably haven't seen this one before. So for the greatest integer function, all that means is you are looking at the greatest integer up to a certain point on the graph. One thing you always hear about the greatest integer function or the step function is you always round down. So if I said, what is the greatest integer function up to 3.7? Well, that would be 3, right? Because 3 would be the greatest integer up to this point on the graph. If you look at these guys, so here's kind of what this means. If we said, what is the greatest integer function for everything up to 1, right? Then we would say, well, here's my greatest integer function is 0 all along these values until I hit x equals 1. As soon as I hit x equals 1, I'm up to the next step, right? And so now these guys represent the greatest integers for 1 all the way until I get to a value of 2. As soon as I hit a value of 2, I'm up to this guy. And now these represent all the greatest integer values of 2 until I hit the next value. So that's why this is kind of a good wording for it. It's the greatest integer up to that point on the graph. This is graphable in your calculator, so let me just show you that really quick so you know how to do some of this in your calculator if you have one of these graphing calculators. So go to your y equals button, and if you look at this, this symbol that you see right here represents our greatest integer symbol. You're not going to see that symbol on the graph, but we still have it in the graph. If you go to your math button and go over to the number column, you're going to see it right down here at option 5. So this is for the greatest integer function. So just hit enter. And for now, I'm just going to put an X in there and go ahead and hit graph. And so you're going to see that same step function, our greatest integer function, that you're seeing on my page. So I'm still using our common window of -10 to 10 on both axes. And so you would see this one. We can manipulate this graph a bit. If you were to, say, wanted to graph something a little more involved like this, to see this on your calculator, just go back into y equals. Let me get rid of this one. So I'm going to start by typing in whatever comes first. So I would have to hit the 3 first. Then I need the greatest integer of x. So this is where I would hit my math button, go over to the number column, and choose option 5. And this is where I would put in the x, close off that parenthesis, and now I can type whatever would follow. So in this case, a +2. And so what you're going to see on this is a couple things. One is I'm going to see the same greatest integer function that I had here, but now I'm only going to see it in multiples of 3. So instead of going every single value, it's going to go from starting at 0, but then it's going to go in multiples of 3. So the next one I'm going to see isn't going to occur until a y value of 3. So you're going to see a much bigger gap in between these, right? It's going multiples of 3 instead of multiples of 1. You're also going to see everything get shifted up too. So let me go ahead and hit graph on this. So here's what that would look like. So again, you can see the spacing on this is now multiples of 3. Instead of every single unit, now it's every third unit. So multiples of 3, and it's no longer starting at 0. It's now starting at 2. So everything has been shifted up 2. So it starts at the point of 2, and then the next one that you would see wouldn't occur till 3 values higher, right? Multiples of 3 because of this guy. So we can do all that on the calculator. Let me show you some of the types of questions that you would get asked from this. So just based on our most parent function image of our greatest integer function. So first of all, what type of continuity does it have? And that comes back to this guy that you were seeing right here. So if it's discontinuous, we're going to say which type of discontinuity it is. If it's continuous, we just say it's continuous. And so if you look at the continuity question, obviously it is discontinuous. And which type of discontinuity does it have? This is non-removable. Because there's a clear break in the graph, it's not just a hole in the graph, there's a clear break in the graph. And so that's our non-removable discontinuity. What is the limit as x approaches 1? So we can answer these questions about any graph. I just wanted to show it to you on this one since this is probably a new one for us. So what is the limit as x approaches 1 of the greatest integer function? So as we approach 1, so here's our value of 1. Notice this doesn't say from the left or from the right. It just says 1. So I have to look at both sides of this. As I approach 1 from the left, we can see our limit would be 0. But as I approach 1 from the right, you can see our limit would be 1. So because they are different answers from the left and from the right, we would say that there is no limit as x approaches 1. So it does not exist on this one. If we only limit it to one side, then we would have a value for that. So again, as I approach 1 from the left, So as I approach 1 from the left, you can see that we are at a limit of 0. And again, as I approach 1 from the right, you can see I have a limit of 1. And so if it's given to us as a specific side, then you can have a limit. But in a case like this, it doesn't exist if you just said what's the limit as x approaches 1. Again, you can do this from any function. So let me just throw out one real quick, just to give you another example. If we were to do just our basic tangent function on something like this, and let me tighten up the window so it's a little more clear. So here's our tangent function. Again, you can see our tangent function is not a continuous function from negative infinity to positive infinity, but it is continuous within certain parts of the graph. On this one, if we were to say, what is the limit as x approaches 1? Well, as I approach 1 from the left, you can see that my limit is a value of 1. As I approach 1 from the right, I also get a limit of 1. And so this one, which is also f of x equals 1, or f of 1 equals 1. So this one is continuous, and it would have a limit of 1 since I get that same limit as I approach 1 from the left and from the right. So you can do this with any graph to answer questions like this. Let me give you one that comes up similar to one that comes up in our homework assignment. If we're given a case like this, again, you could graph this and look at the graph to answer this question. I'll kind of show it to you both ways. Let me answer it without the graph first, just so you can see how we would do this. If we said on this function, what's the limit as x approaches 2 from the left, think of your basic greatest integer function first. If we said what's the limit as x approaches 2 from the left, so here's our value of 2. So as we approach 2 from the left, you can see that my limit is 1. And so on this one, if I put in a value of 1 right here, then I could say, okay, well, I have a value of 1 times 3 plus 2, and I would get my limit equals 5 in a case like that. If you just graph this whole thing and did this without the parent function, so we could do it that way as well. You see we should still get that same limit of 5. Let me go back to what I had on here. So I'm going to go back to typing that in of 3. We're going to go to math, go to the number column, get our greatest integer function, which is option 5. And put the x back in there, close that off, plus 2. So if we go back to that greatest integer function, which looked like this, now if we said what's the limit as x approaches 2 from the left, so right here, you can see as x approaches 2 from the left, you can see right here we're at a y value of 5. And so again, I get that same limit of 5 by looking at this function from the graph. And so we could really take either approach. So we could look at it from the graph, or we can just base it on our knowledge of the parent function and then apply those numbers to our answer. So we could do that one either way. So let me flip to the next page on this. And we're going to take a look at some more one-sided limits on these guys. So for these guys, these are ones that are more involving infinite limits, like this one here. So here's kind of where you know this would come up. All these guys revolve around having asymptotes within your graph. So whenever you have those asymptotes, your graph is either going to be headed forever up or forever down as it approaches that value. So on this one, we would know that we have an asymptote at 4 because that would create our undefined value within our denominator. So we couldn't do a direct substitution with 4 because it would create that 0 denominator. So we know there has to be an asymptote at that point. As we've talked about before, it can't be a whole at that point because nothing cancels. There's no common factors that would cancel that out. and give us a value that we could work with. So if it doesn't cancel out, we know it's an asymptote and not a hole in the graph. So as we look at this guy, if we said, what is the limit as x approaches 4 from the right? Again, we're just trying to figure out, is our graph approaching positive infinity or is it approaching negative infinity? So let me show you this one as the graph first. So hopefully that will make a little more sense. So if we go to our x over x squared minus 16, so here's what this graph would look like. So right here is where you're seeing x equals 4. So you can see there's a clear asymptote right there. And on the graph, this answer is super obvious. As I approach 4 from the left, I can see that my graph is headed towards negative infinity. And as I approach 4 from the right, I can see my graph is approaching positive infinity. So the limit at 4 does not exist, right? But we can still define what the graph is doing on either the right side or the left side. So if it just said what's the limit as x approaches 4, and there was no sign right here, we would have to say it does not exist. But if it's just talking about what is happening to the graph on either the right side or the left side, then we can identify a limit as either positive or negative infinity. Again, that's not really a true limit since infinity is not an actual value, but it becomes an accepted answer because we sort of see it as a description of what the graph is doing, even though it's not really a true limit of what we're getting. So anyway, if we're looking at the graph, answer becomes super obvious, but if you don't have the graph to look at, or if we're not able to use a calculator for a case like this, then we can do a little number testing here to see whether it should be overall positive or overall negative. Because this one is approaching 4 from the right, I could test any number greater than 4 to see what kind of a sign I'm going to get out of this. So let's just pick a number like 5. So if I put a 5 here, obviously that's positive. If I put a 5 here, or any number greater than 4 here, I also get a positive. So any positive divided by a positive is an overall positive. And so that's how we know we're going to get a positive infinite limit, everything to the right side of 4. A couple things you can sort of see for this one. So again, we started by checking direct substitution. Couldn't do it because it would be undefined at that value. So from there, we want to go into relating it to its asymptote. So because we know there's an asymptote right here, again, now we're just checking the signs to see if it's headed towards positive infinity or negative infinity as it approaches that asymptote. And again, here's kind of a key on this, is we're only using positive or negative infinity as a limit if it's a one-sided limit. So it's got to be a plus or a minus right here in order for that to happen. So let me go down to some piecewise functions or hybrid functions like you're seeing right here. So in this case, now we have two different functions completely, but this one only exists for x is less than or equal to 3. And this function only exists for everything to the right of 3. So we have two completely different functions. So it kind of depends on what value we're working with to see which function I should be taking a look at. So again, a lot of this has to do with just being able to work with numbers without having a calculator or a graph in front of you. If I were to graph these two separate functions, it would just be another way of looking at it. We would see the continuity much more simply by looking at those graphs. But these are cases where we don't have the graph to look at, so we got to do a little number testing on these guys. So for this one, if we just said, what is the limit of the function? So here's our overall f of x function as x approaches 3. So this one is giving us just that value of 3. So we have to test, like we did in earlier lessons, what is the limit as x approaches 3 from the left and from the right to see if we get the same value on both sides. If we get the same value on both sides, then we have us a limit. If we don't get the same value from both sides, then we have to say it does not exist. So we are taking a value of 3 and we're plugging it into our functions. but which function depends on whether we're approaching it from the left or if we're approaching it from the right. So limit as x approaches 3 from the left, so I am doing a direct substitution on this function as I plug in a 3 right here, since we're approaching it from the left, and that's what fits this domain. So if I plug in a 3 for that one, I get a limit of 2.5. But if I said, what's the limit as x approaches 3 from the right? So again, I'm still doing direct substitution, but now because of this domain and approaching 3 from the right, I got to plug it into this function. So if I put a 3 right there, I get an answer of 2. So because these are different, I get different limits as I approach 3 from the left and approach 3 from the right. We'd have to say it does not exist. All right, stay with me for one more here. I got one last thing to show you. So looking for x values where f is not continuous and which ones are removable. Discontinuity. In other words, which ones would create a hole in the graph. So it would not be continuous anywhere I have a hole or an asymptote. I know my graph is not going to be continuous at those points. So if I put this in factored form, so take a look at it right here. So anything that would create a 0 in my denominator is where my graph is not continuous. So at 0 and at positive 1, I know my graph is not continuous. So which one of those is removable? Well, the one that factors out, the one that cancels, is where we would have a hole in the graph, and so that one is removable. Remember, if it doesn't cancel, like this one doesn't cancel, you would have an asymptote right there. So based on these zeros, I know this one is a hole, I know this one is an asymptote, and the hole is the one that is removable. So that's where x equals 0. And that's it for part 1.